the target applications that we're trying to implement, but also typically reflecting the legacy of the design or the designers that need to be comfortable with these. I'm going to talk specifically about some work that Tensilica has been investing in significantly, in not just thinking about individual building blocks, but in fact now implementing an LTE reference architecture. That is, an efficient handset implementation for multiple modes of the LTE spec, targeting low power, low cost handset and data card implementation. I'm going to use as an example drilling down on one particularly hard problem. So, turbo decoding is a now popular standard for the encoding and decoding of information to make it tolerant of the noisy wireless environment. And it's an incredibly computationally intensive task.
That turbo decoding, it existed in the 3G world and now it's going over to the orthogonal, or?
There are flavors of it that have been used in some UMTS. It certainly appears in HSPA+. It's evolved somewhat. So the notion of turbo coding has been there before. What makes this particularly hard is that the data rates for LTE are so high, so that if you compare it to HSPA+ at a few tens of megabits per second, Cat4 by 2 Mimo receivers are now talking 154 megabits per second. Turbo decoding takes on the order of 5,000 or 6,000 operations per bit. So, because it's this iterative algorithm to essentially converge on a best estimate of the transmitted signal. And you take 6,000 operations per bit times 154 megabits per second. You're talking a lot of ops, more than you're going to do on a conventional processor. To date, almost everyone has done this as a specialized piece of hardware. We actually have figured out some very clever ways to make rather specialized processors that achieve similar efficiency but do it in a somewhat more flexible and programmable fashion. And then we'll talk about methodology and tools, both an overall view of how you take this notion of using processors and RTL blocks and a specialized instruction set extensions together, and how, in particular, we integrate this with Synopsys tools, and therefore how it relates into some of these modeling infrastructures like the steepest descent model set. So when we look at the wireless world, in particular when we look at baseband processing, we see three megatrends, if you will. One, there is the trend towards much more performance-intensive standards. If you look at the computational load implied by the evolution from 2G to 3G to 4G, if you look at the power level, and you look at the operations rate in terms of billions of operations per second, you see something in which we have the lovely combination of the computational rate going up by 2 orders of magnitude and the power budget going down by a factor of 3. That's a computationally hard problem. That means that as a community we need to innovate much more rapidly than Moore's Law. Moore's Law is not going to solve this problem for us. Moore's Law does not give us 300 to 1,000x improvement over the course of just 2 generations of wireless technology. And so there's enormous demand for innovation in architectures and implementations. The second megatrend is a drive towards multi-standard. This is true certainly in the wireless area, where you typically have not only multiple modes within one standard, but coexistence in one piece of silicon with multiple standards. So your 4G phone will still make 3G calls. It will still talk to a 2G network as needed. And this is even more dramatic when you look at standards like digital video broadcast, where in different parts of the world you see different kinds of alphabet soup. So In Europe, you have DVB. In North America, you have ATSC. In Japan, Peru, and Brazil, you have ISDB. In China, you have DMB. And other parts of the world are either assessing standards or multi-standards. So anybody who's building hardware platform, in particular if you're building a silicon platform, you have to be thinking about how you build one chip that operates on all the different standards. And that means a push towards more programmability and flexibility in everything that you do in that complex processing. And finally, even if you're not building low-cost portable devices, the push towards low-cost green infrastructure means increasing attention to power efficiency of these devices. In fact, if you look at communications and computation infrastructure, the cost of electricity is becoming comparable to the capital cost of the equipment itself. And so one of the most important ways that people are able to save money and build more competitive products is by building lower energy products. So let's look a little bit about the evolution of the cellular standards. You're generally aware of the whole 2G evolution from GSM to GPRS, Edge, WCDMA, and up into some of these high data rate 3G standards like HSPA. Then there is, if you will, let's call it the Qualcomm series from CDMA and EVDO, which have progressed in terms of data rate. And in China, you have the TDS-CDMA standard. Now, interestingly, all the world appears to have converged on LTE as the next generation, albeit in somewhat different forms. Frequency division duplex here, time division duplex in China. But there is an opportunity for convergence, and that means that there's a great deal of investment around the world in LTE-based systems. Terminals, handsets, data cards, cell phones, very wide variety, picocells, femtocells, macrocells, all being designed.
Where is it?
Yeah.
Yeah, I'm sorry, Chris. I've seen the picture where I knew that GSM and CDM were converging. The Chinese are coming in too?
Yes. The Chinese have basically said, TDS-CDMA was our 3G solution. China Mobile has said, we're going to do LTE for 4G.
So I'm assuming royalty issues and all that kind of stuff have disappeared from their mindset in the LTE stuff? Or
yeah, LTE is more benign. LTE is more benign from a royalty standpoint, which is part of the reason why they're no longer going to go their own road. I think they found that this was a pretty expensive proposition. It may be royalty.
It may have been royalty
free,
but there was engineering time that took over.
Right.
Got it.
Yeah. So there are two fundamental technologies in LTE which make it hard. One is the adoption of OFDM, which means that you're doing much more of the work in the frequency domain. This is a technology that's been widely used in other kinds of communication standards. So 802.11, DSL, DVB all use OFDM fairly widely, as does WiMAX. But it puts enormous pressure on things like the rate and efficiency of doing fast Fourier transforms. The other is the adoption pretty uniformly of Mimo, which essentially has higher spectral efficiency. That it gets more bits through the same amount of spectrum by essentially using multiple antennas and multiple receivers. But it is also much more computationally intensive to receive Mimo signals. And that also changes the nature of what you have to design into the hardware. And so because of this growth in computational complexity, the traditional design approaches are not going to simply scale incrementally up to the LTE level. The desire for more flexibility to handle all of these different modes and the fact that you've got an order of magnitude more computation mean that an LTE design may sit next to a 3G design on a chip, but it's probably not possible to just add a few bits and pieces to a 3G design and say, okay, now I've got everything I need for doing 4G. So let's look a little bit inside of what one of these modern OFDM, MIMO-based data path looks like. If we take a receiver just as an example, you typically have an analog to digital converter. You have various kinds of filters which take place, which precondition the signal and do synchronization functions, do frequency and phase offset, gain control. And then you go into the FFT, which is going to put you into frequency domain processing, allows you to select out those little boxes that Frank talked about in that big map of time versus frequency domain, so that you can deal individually with the signals associated with each of those fine boxes. Though there is a level of synchronization, decoding that has to take place there. Plus, you've got actually quite complex control channels. Some of those colored boxes in Frank's chart really represented the control signals that don't deliver the data, but set the mode for everything else. And because there are so many modes, there is actually quite a bit of data flowing through this channel. In fact, the control processing alone is comparable to what you would find in 3G. And so 4G, with its very high data rate, that's 150 megabit per second, is then on top of that large control processing. Then you have MIMO decoding and demodulation. This interacts quite closely with channel estimation. Channel estimation is basically that process of taking certain of those colored boxes which represent pilot and reference signals and using those essentially as a way to sample what is the distortion and noise which is taking place during the transmission. What happened to the transmitted signal? So that then you can apply those correction factors to the signal that you're trying to decode and demodulate here. MIMO decoding is this process of taking not just a single set of samples, which is typically some complex number, but essentially taking a vector of complex numbers and doing the processing on it, where the channel becomes, in fact, a large matrix. And the convergence towards a best estimate of that signal using MIMO decoding invites a wide range of different algorithms to be used. And one of the places of greatest variation and value add within a receiver is going to be in exactly how the channel estimation is done and exactly what level of aggressiveness in MIMO decoding is applied, because the computational load for those things will vary by as much as 2 orders of magnitude, depending on how aggressive you're being in MIMO decoding. And then you get to forward error correction. So this is the process of using the redundancy in this signal to overcome injected errors. And this is where, in particular, turbo decoding is used in the data path, and more conventional Viterbi decoding is used in the control path. And these are the reasons why, because the main data path is so computationally intensive, you need to have specialization. In the control path, you have so many different modes, so many different kinds of control information that a high degree of programmability is required at significant computational rates. So what are some of the problems that the designer of a baseband faces? And we could oversimplify here and highlight 4 categories of problem that this designer of a new LTE baseband might be up against. First, they may have solutions to current radio standards, but their job is to have an up-to-date LTE-based solution. And they have to decide, well, am I going to reuse those existing blocks, which may have the advantage of already have been verified and certified, and have those coexist with an entirely new LTE design? Or do I want to do a design which is programmable across 3G and 4G standards? That will be an important question to answer early on. Second, there's a question of design style. The historical design style, the dominant design style for 3G designs, was one in which you may have had a relatively modest digital signal processor, but then typically you had lots of accelerator blocks that were used for specific data processing functions in both decoding and in demodulation of the signal. They may have been controlled by that DSP. They may have been controlled by other small RISC controllers that were essentially setting them up or feeding them data and commands, but where they were really just hardwired data paths of computational elements. What we have seen, though, is that because of the number, the bandwidth, and the required flexibility of those blocks, you can't just add on more hardwired accelerator blocks and expect to get the same result. You need to think about how you increase the level of throughput and flexibility. The third problem is that the designer may have historically used DSP cores, but the level of throughput required is now much, much higher than what those historical DSPs can provide. Or, final problem, that even when the designer is working mostly in the software domain, perhaps building their own DSP processors, and this is certainly true in the largest semiconductor companies, that they may have outgrown their tools, that the level of complexity of the software is such that you need world-class compilers and debuggers and simulators. Homegrown DSP tools aren't adequate. So, yeah.
Right now in the LTE standards, there's some interesting stuff going on. I shouldn't say it's the LTE standards, it's the business models that the carriers are deploying. And
right.
Particularly, they're saying, I love 4G and LTE for the data side. Voice side, not so fast, grab it.
Right.
I want to leave things where they are.
Right.
What's the implications in if you sit there and your DSPs need to support the data, in effect, are you having to do a retrofit? Or is there a situation where you guys see a dual design going on internal to the device?
What we see as the default assumption is dual design. They're going to retain the existing building block, at least for now, because it's the shortest path to market, and they're going to add the LTE alongside of it. Because the current generation was designed in current semiconductor technology, it does get smaller as it rolls forward to next generation silicon technology. However, we do see that people who are doing that ultimately want to get to the smallest, most flexible solution. And so there is an anticipation of the integrated, programmable, all-in-one over time.
Got it.
So let's talk briefly about what we see going on computationally. There's lots of different ways of measuring this increase in performance. Even if you ignore forward error correction, going from 2G, so call it GSM, to LTE is something over 100x increase in the operation rate. If you were to look at forward error correction computation, that might be 1,000x increase over that same sequence from GSM to LTE. And it's interesting how this has affected the preferred implementation. 2G was low enough performance, you actually could do most of the work on a DSP core. In 3G, more and more of the work had to be done in function-specific coprocessors. So if you look at how many ops per second were required, 80 or 90% of the ops per second were actually done in hardwired execution units, not done in the DSP. When you get to 3.9G and 4G, and here I'll use the nomenclature of LTE being 3.9G and LTE advanced being 4G.
So you're building for Japan.
Huh?
You're building for Japan.
Why do you?
No, they always say it's not really 4G, it's 3.9.
Yeah, right. Well, we run into some purists who sort of say, well, 4G is reserved for things that go up to, round off to a gigabit per second.
Right, exactly.
Yeah. So we think that this concept of data plane processing units, which are programmable engines that are more specialized than generic DSPs, is really the way to go. And I'll be talking about that. Just as an example of what a 3G design looks like, here's a picture of Infineon's X-Gold 608 product, just so that you get an idea of what they've put on here. This is a fairly highly integrated chip. And in fact, you see that some of these 3G accelerators, like the eGPRS and the UMTS accelerator, they are much larger in significance, and that probably means physical size, than the DSP. So the DSP is a relatively small player in this, that other functions are really playing a dominant role in this, just as there are also some accelerators for 2G, for encryption and ciphering. So multiple cores, RISC controllers, large RTL blocks, small DSPs.
The secure boot code, is that the IMSI, or is that something even more proprietary internal to each company?
I'm sorry, which?
In the middle, there's a secure boot code, if I'm reading.
Oh, yeah, okay. Secure boot code here. I think that generally there is a requirement in these platforms which are now complex enough that they have downloadable code, is that there needs to be some kind of security mechanism. The specific mechanisms that different companies use to ensure that they are able to isolate the boot code that's required for fundamental functionality from code which is add-on applications varies.
Right, but it's not the thing. I can't expect that they're going to replace the SIM chip anytime soon with this code. This is a network operator type code.
Yeah.
Got it.
So, what does Tensilica put its focus on? Here's a picture that represents sort of a hypothetical system on chip. And increasingly, the world does look like this kind of all-in-one device that has various kinds of analog interfaces, has some big application CPU, has a lot of general-purpose memory, and then has quite a number of different subsystems: video, audio, baseband, security, protocol processing, and the like. And it is in these data-intensive, complex subsystems that Tensilica puts its focus. Tensilica is a supplier of processor cores and software. I think we've recently been recognized as the fastest growing of the top 10 IP suppliers in the world for semiconductor IP. And it really reflects the fact that the world has more problems in this category. And that is not an area being served by the ARMs and MIPS and other traditional kind of application CPU providers. So we're using the term data plane processing units, DPUs, to really reflect the category of processors here which are found in the data plane, which have characteristics of DSPs and CPUs. DSPs in the sense of being highly tuned for computational throughput. CPUs in the sense that they often are running very complex control structures, lots of interrupts, they run operating systems, they have lots of multiprocessor support requirements, they need very sophisticated software tools and debuggers and simulators in order to be productive for the potentially millions of lines of code which are found even in the data plane, even setting aside what you'll find on an applications process. So just to give you a little bit of a sense of what do we mean by a data plane processor and what does it mean to automate the generation of data plane processors, here's a picture of how that process actually works. So our user is a designer of system on chip. They're an architect or a software architect or their hardware architect who is looking at a particular subsystem within that overall chip and saying, I have certain computational requirements. And I'm going to configure a processor by some combination of selecting from a menu or adding additional instructions on top of some reference template, or to automatically discover the optimal set of instructions and interfaces that I need. And all of that processor configuration goes into the processor generator, which creates the complete hardware design of that processor subsystem and the complete software tools that reflect the precise set of choices here. So you could do something as simple as say, well, I need a general purpose mid-size RISC controller or a general purpose 2 Mac per cycle DSP. And those are simple choices from the menu. Or you could say, I want a processor that not only does all of that, but I need something which is going to specifically implement the add, compare, select operations required for Viterbi. Or I'm going to do this massive state update associated with Turbo, or I'm going to add special instructions that allow my FFT to run extremely fast. And those are all typical operations that you would do in configuration here. And of course, because it is a real, fully programmable processor, you expect both completely verified RTL scripts for running the EDA tools, test environment, and you expect complete software environment. So you expect, if you've specified a processor, that all of those instructions are recognized by the compiler, it's in the simulator, it's recognized by the RTOS, it plugs into system modeling environments like the System Studio and Innovator environment that Frank here will talk about shortly. And then it becomes this element to be able to be a subsystem within the chip with a very high degree of confidence that this processor and its software will do exactly what you want. And it's also important to understand the time constants here. And let me be fairly precise about that. The time to change the instruction set of a processor that you're designing, that is, to rebuild the software, to rebuild the models, to rebuild the estimates of the hardware, is about 5 minutes of processing time. And literally, you sit there on your desktop and you're iterating through many possible instruction set options. If you want to go from scratch, completely new concept of a processor configuration to complete generation of RTL, that is about 2 hours of processing time. And as a result, what you find is that the designers are able to explore a much larger space of possibilities in the instruction set and interface and algorithms than they would in a conventional processor environment or in a conventional hardware design environment. And that changes the productivity and really expands the role for these optimized processors within the block diagram of these wireless system-on-chip designs. So I'm going to now drill down even further in terms of giving you sort of the Gray's anatomy of an extensible processor, where I'm going to take as a reference one of our more sophisticated lines, the Extensa LX2, and talk about the different pieces. First of all, there is a base processor. This is not a blank sheet of paper. In fact, all of the Tensilica processors implement the Extensa baseline instruction set, which is the instruction fetch and decode, the base execution, the core register file, the ALU, the interfaces to instruction and data memory. And that irreducible minimum is only a few thousand gates, but guarantees that any processor that you configure or create will run the same baseline RISC code. So the operating systems and the libraries and all of the kind of common code runs without any change whatsoever across all possible Tensilica processors. So it's a compatible foundation. Then you get to configure what you need for your application in, for example, the memory system. So you can have any combination of instruction cache and RAM and ROM and data cache and RAM and ROM, and bridges to all of the popular system buses, complete configurability of memory management, ECC, and parity protection, depending on what the requirements are from the system and the trade-off between performance and cost in your application. Then there are a wide variety of predefined but optional subsystems. These are things that Tensilica has specified. In fact, we specify it in a language called the Tensilica Instruction Extension, or TIE language, which then allows you to simply click and add multipliers, dividers, floating point units, complete vector DSP units, audio DSPs, as well as a wide variety of system peripherals, timers, interrupt controllers, debug support, trace ports, exception support, and even external units like full PC trace, so that you have exceptional insight into the real-time behavior of your system. And then finally, there are the things that the user defines. Using exactly that same high-level description format, TIE, you can describe new execution units, new pipelines, new issue slots within a VLIW instruction execution, and new ports to the processor. This is particularly important when you start thinking about how a processor gets integrated with other blocks of hardware within the system. What it means is that you're not just limited to talking over the system bus to other parts of the system. In fact, you now can create custom ports which match exactly to the I/O characteristics of RTL. You can use Q interfaces to talk to memories, or most especially talk to other processors, essentially providing hardware message passing, or can implement special memories, any number of special memories, so that you can have extraordinary memory bandwidth, thousands of bits per cycle of memory reference in an extended processor. And as a result of these kinds of capabilities, it's really a family of processors that extends well beyond what any conventional DSP or CPU can do, because it's much more closely tuned to the computational demands and to the I/O demands of a particular design scenario. When we talk about the application of this kind of technology into wireless systems, we face an inevitable set of trade-offs. On one hand, people want very high energy efficiency, very small area, lowest possible cost. So they're really talking about efficiency. And typically people have gravitated towards hardwired data path design for those. On the other hand, people also want to maximize adaptability and programmability. In that case, they often migrate towards traditional DSPs. And really, this has represented a set of trade-offs here. What we're really seeing as we move towards these DPUs is that it's, first of all, operating, if you will, on a higher plane. That is, there is a better overall set of trade-offs between the two. But even within that, even as you have more efficient, more programmable engines that come from this optimization, you still have a range of choices. At one end of the range of choice, you could have still baseband oriented but fully programmable and fairly general purpose DSPs. Or you could say, I really want to have more finely tuned accelerators, programmable accelerators, perhaps in conjunction with multiple small processors. And what we tend to see is that in base station designs, we'll see people doing things that just look like better DSPs. And in handsets, we'll tend to see people who are really thinking about designs which are similar to what they would have done in hardwired, but are now more programmable. So the migration tends to be from upward in performance and efficiency from traditional DSPs, and across in adaptability from hardwired. Now let's think about how one potentially integrates existing accelerators. And so by accelerator here, I mean some hardwired data path design that may have been designed in Verilog or VHDL, and which has a set of interfaces to it. Data gets streamed in, data streams out, it's got a set of commands, it has configuration registers. It may be a fairly complex subsystem here, but not highly programmable. Its programmability really is in the form of what data and commands flow into it and how these configurations of registers are set. But if you look at the pins of this kind of a thing, you tend to see that there are these input and output streams, command streams, input and output flags, and configuration registers. Well, it turns out that when you start connecting this up to some controlling element, a processor, you have the potential, using this Tensilica instruction extension mechanism, this configurable interface, to specify interface